Hello friends, welcome back to Rising Mathematics. In this video, we are going to solve this exercise question from book Contemporary Abstract Algebra by Gallian. This result is also known as law of exponents for an Abelian group. So, the result is let AB be elements of an Abelian group and let n be any integer. Show that ABN is product of A and Bn. We have to check whether the given result is true for non-Abelian groups also. Now, as we want to show the given result is true for any integer n, we have three cases. First one will be n is 0, second one will be n is a positive integer, and third one will be n is some negative integer. So we are going to prove the given result for these three cases. We will start our proof. So our case 1 is n is 0. Then we have AB0 equals to identity, and also A0 B0 will be identity. So AB0 equals to A0 B0, and this shows that the result is true for the case n equals to 0. Next, case 2 will be n is a positive integer. So to prove that result is true when n is a positive integer, firstly we will show using induction on n that for all elements AB of group G, ABN equals to BNA. Now for induction, for n equals to 1, it is clear that AB equals to BA. Since our group G is abelian, so for all elements AB in group G, they will commute. Hence we have AB equals to BA. Now suppose that for some positive integer n, we have ABN equals to BNA. Then ABN plus 1 can be written as ABNB using associativity in group. Again, this ABN can be written as BNA since we have assumed this thing for n. Again, using associativity, we can write this as BNAB. Now this AB can be written as BA, so we get this. Finally, using associativity, we get ABN plus 1 equals to BN plus 1A. So, we have assumed that the result is true for some n, and we have shown that it is also true for n plus 1. So, using induction, we have proved that for all elements AB of group G, ABN equals to BNA. Now, we want to show that ABN equals to ANBN for every positive integer n, and we are going to show this thing again using induction. So for n equals to 1, we have AB1 which is AB which is A1 B1. So result is true for n equals to 1. Now assume that the result holds when n is some positive integer, that is ABN equals to ANBN. Then we get ABN plus 1 can be written as ABN AB. Again, this ABN we can write it as ANBN AB since we have assumed this thing. Again, using associativity, this can be written as ANBNAB. So we will replace this BNA by ABN as we have shown this thing. So we get this expression. Again, using associativity, we get AN plus 1 BN plus 1. So we have shown that when n is some positive integer, we have ABN equals to ANB, and then for n plus 1 we will get ABN plus 1 equals to AN plus 1 BN plus 1. So by induction, for all positive integer n, this result is true. Now our last case will be n is a negative integer. Note that AB equals to BA will imply and is implied by A inverse B inverse is equal to B inverse A inverse. By just taking inverses on both sides of this expression, we will get this, and similar thing will happen here. Now as n is a negative integer, n can be written as minus mod n. So we get ABN can be written as AB minus mod n. Now we can write this as AB inverse mod n. Then using Sokshue property in groups, this can be written as B inverse A inverse mod n. Now from here we can replace this B inverse A inverse with A inverse B inverse mod n as it is. This can be written as A inverse mod n B inverse mod n, which can be written as A minus mod n b minus mod n, that is a n b n. So we have proved for some negative integer n that a b n equals to a n b n. So our result is true for every integer n. Now in the question we have asked to verify that whether the given result is true for non-abelian groups also. So answer is no, and we will prove this thing through one example. So our example is group of quaternion groups, which is a non-abelian group having 8 elements. Elements of Q8 are 1 minus 1, I minus I, j minus j, k minus k. Now here we will assume that A equals to I and B equals to j. Then we get AB square equals to I dot j square. Here binary operation is multiplication. Now I dot j is k, so AB square will be k square, which is minus 1. And a square dot b square will be I square dot j square, which is minus 1 dot minus 1, which is 1. So clearly AB square is not equal to A square b square, and thus result does not hold for non-abelian groups, which is shown by this example, and this proves our complete result.